Hello, today we're going to talk about complex numbers. So, our goal is to make sure that we learn basic concepts about them and learn operations on the complex numbers. So, in order to to talk about this idea, what we're going to do is we're going to consider the equation x squared plus 1 equals 0. If we are to solve this equation, then what this gives us is x squared equals negative 1. Now, to extend the number system to include numbers such as the square root of negative 1, because that's what we would get if we would go ahead and finish solving this, then what we have to do is we have to introduce a new number into our system given by I, and we're going to call that an imaginary unit. So, in fact, I squared is equal to negative 1, right? I squared is equal to negative 1, and I is equal to the square root of negative 1. So keep these in mind because you want to use this throughout this section. Now, definition. If a and b are real numbers, then the number a plus bi is a complex number and is said to be written in standard form. Okay? Now, if b is equal to 0, if we write b is equal to 0 in this part, then the b times I is going to disappear. So we'll just get a, and that is just a real number. If b is not equal to 0, then the number a plus bi is called an imaginary number. A number of the form b times I, that where b is not equal to 0, that's just called a pure imaginary number. That's called a pure imaginary number. Okay? Now, the equality of complex numbers. Two complex numbers, a plus bi and c plus di, are said to be equal to each other, meaning if we have a plus bi equals c plus di, that happens if and only if a is equal to c and b is equal to d. That's only if their real parts are the same and their imaginary parts are the same. So a equals c, that's an a here, a equals c, and b is equal to d. Now, you can add, subtract, multiply, and divide complex numbers. So to add them, you add the real parts together, and then you add the imaginary parts together. If you're subtracting a plus bi, or if you're subtracting c plus di from a plus bi, then you get a minus c plus b minus di. And in fact, if a is greater than 0, then the square root of negative a, remember, is equal to the square root of negative 1 times a, all of that underneath the radical. That's equal to the square root of negative 1 times the square root of a. But the square root of negative 1 is I from the first page. So that's equal to I times the square root of a. Now, using this fact above, we're going to go through an example where we're going to write the following as the product of a real number and I. Let's start out by going through the square root of negative 81. That's equal to the square root of negative 1 times 81, but that's equal to the square root of negative 1 times the square root of 81. That's just equal to I times 9, or 9I. That's it. Now, you can pause the video and work through the example, the square root of negative 98. I'm going to go ahead and go through that, but you should pause it and work through it on your own. Here, using this rule, here we get I times the square root of 2 times 49, because there's a perfect square in 98, and that's equal to 7I times the square root of 2, since the square root of 49 is equal to 7. The square root of 49 is equal to 7, so that comes here, and then times I, which is already there, and then you're left with the square root of 2. That's it. Now, a rule of thumb to remember: simplify before you multiply. Simplify before you multiply. And this concept is very important, so remember this. Now, let's simplify the square root of negative 42 divided by the square root of negative 3. Well, that's equal to, by our fact on the previous page, that's equal to I times the square root of 14 times 3 divided by the square root of, or I times the square root of 3. Now the reason we factored 42 as 14 times 3 was because we saw this 3 already there in the denominator underneath the radical. So now what you can do is you can cancel your i's, and when you cancel your i's, you're left with the square root of 14 times the square root of 3 divided by the square root of 3. Now the square roots of 3's, they cancel, and you are left with the square root of 14. Now we're going to go through another example where we are going to write the following: 15 minus the square root of negative 75 divided by 5 in standard form a plus bi. So we'll take it step by step. Let's start out by writing the original problem down. So that's 15 minus the square root of negative 75 divided by 5. That's equal to 15 minus, now we're going to use our fact because we have a negative underneath the radical. So that's minus I times the square root of 75 has a perfect square in it. It's 25. So write this as the square root of 25 times 3 divided by 5. And this is equal to 15 minus 5i times the square root of 3, divide that by 5. Now, if we look at our term in the numerator, you have 15 minus 5i square root of 3. These both have a 5 in common. We're going to factor that out because we see a 5 in our denominator. So that's equal to 5 times the quantity 3 minus I square root of 3. We factored 5 out. Now we can cancel those 5's. So that's equal to 3 minus I square root of 3. That's our final answer. Now we're going to go through an example where we're going to find the sum of two complex numbers. So we're going to find the sum of 4 plus 7i plus 1 minus 6i. Well, you add your real parts together, meaning you add your 4 and your 1. What do you get? I'll write the steps in here. So you have 4 plus 1 plus 7 minus 6 times I. That gives you 5 plus 1i, or 5 plus I. Now we're going to go through an example where we find the difference. So we're going to find the difference between the following complex numbers: 3i minus the quantity negative 2 plus 3i minus 2 plus 5i. And remember, with all these examples, you should always pause the video, work through them, and then press play to finish hearing how to do it. Okay? So this is equal to 3i. Distribute your negative here to each part. So you have to distribute the negative to this term and to that term, and distribute this negative to this term and to that term. Doing that, we get plus. So now we're going to add to this plus 2 minus 3i minus 2 plus, nope, that should be a minus because we're distributing our negative. So minus 5i. Now, your 3 i's cancel, your 2's cancel, and you are left with negative 5i. Is your final answer. Now we're going to go through an example where we're going to multiply complex numbers. So let's go through this one. We're going to multiply 4 minus 5i quantity squared. That's equal to 4 minus 5i times 4 minus 5i. Using the FOIL method, you have to multiply your first terms together, your outer terms together, your inner terms together, and your last terms together. So doing that, we get 16 minus 20i minus 20i plus 25i squared. That's negative 5i times negative 5i. And now we simplify where possible, and that's 16 minus 40i. I squared is negative 1 from that important fact that we discussed earlier. And so this is minus 25 because I squared is negative 1. So that's equal to 16 minus 25 is negative 9, and then you have minus 40i. So here you needed to recall I squared is equal to negative 1. Okay? Now, let's simplify powers of I. Simplifying powers of I, we have I'll go through two parts here. One, let's simplify I to the 33rd power. So an aside here, you want to keep in mind the basic powers of I. So I squared is equal to negative 1. I cubed is equal to I squared times I. But that's negative 1 times I. So that's equal to negative I. I to the 4th is I cubed times I, which is negative I times I. Negative I times I is negative I squared, so it's negative 1 times I squared, which is negative 1. So it's the opposite of negative 1, which is 1. And then I to the 5th is I to the 4th times I, but that's just 1 times. So I to the 4th times I, that's equal to 1 times I, which is just I. Now I to the 6th would just be I to the 5th times I, which would give you I times I, which is I squared, also negative 1, which repeats. So your powers will repeat. So now all of that to say I to the 33rd is equal to I to the 4th raised to the 8th, because 4 times 8 is 32, times I. Remember the rule that says if they have the same base, you add their exponents. So x to the n times x to the m is equal to x to the n plus m. We're applying that rule here. X to the 4th, if we go back and look over here, x to the 4th was equal to 1. So this is 1 times I, or I. Another example, let's look at I to the 14th power. I to the 14th power is equal to I squared raised to the 7th power. I squared is negative 1. A negative number raised to an odd power gives you a negative 1. So that's what we get. Now, if a definition, if A and B are real numbers, A plus BI and A minus BI are called complex conjugates of each other. In fact, when you multiply them, you just get a squared plus b squared. Why is that? An aside. If we use a FOIL method, you get a squared minus abi, that's your outer terms, plus abi, your inner term, minus b squared I squared. These terms cancel. I squared is -1, so this is a squared minus b squared times -1, but that's just going to give you a squared plus b squared. Okay, so the final example, what we're going to discuss, we're going to go over two examples. One, we're going to go over 2 plus 3i divided by 4 minus 2i, and our goal here is going to be to write this in standard form, a plus bi. So that's equal to, here, in order to simplify this, we need to multiply by the complex conjugate of the denominator in the form of 1. So this is 2 plus 3i divided by 4 minus 2i times 4 plus 2i divided by 4 plus 2i. See, we didn't change the problem because we just multiplied by 1, but we're being clever with our choice of 1. So now we'll use the FOIL method because you're going to multiply numerator times numerator, denominator times denominator. Doing that, we get 8 plus 4i. That's what you get when you multiply 2 times 2i. Now 3i times 4, you get plus 12i. And then your last term, you get plus 6i squared divided by, now we use the fact that we just discussed on the previous page, when you multiply complex conjugates, you just get 4 squared plus 2 squared. So we're going to get now 8 plus 4i plus 12i minus 6 all over 16 plus 4. Simplify. 8 minus 6 is 2, and 4i plus 12i is 16i divided by 20. So that's equal to 2 over 20 plus 16i over 20. Simplify that. You get 1/10 plus 4/5 I. And this is in standard form. And that's it. Now, 2, if we consider 15 over minus I with the same goals, let's write this as 15 divided by minus I times I over I. That's the complex conjugate. We get 15i divided by -I squared, or that's 15i divided by 1. That's equal to 15i, but we want it in standard form, right? So that's equal to 0 plus 15i. Okay, that concludes complex numbers.